Hello, my name is Hans Burgerhof and I work as a statistician in the UMCG. This video is part of a series of videos about medical statistics. In this video I will give you some information about statistical tests for independent groups with an ordinal outcome variable or a continuous outcome variable which is not normally distributed. Let's have a look at the variable time to pregnancy in years for the group of subfertile women who naturally conceived and the combined groups of women receiving IVF, discussed in the article of Jorien Seggers and colleagues. These data are clearly not normally distributed. So to compare the distributions, we cannot make use of the t-test, which assumes normal distributions. What to do then? In some situations we can transform the data to another scale on which the distributions are normal or close to normal. For distributions skewed to the right, we can, for example, use a logarithmic transformation. We can also choose to use another statistical test, one that does not assume a normal distribution. For two independent groups, we can use Wilcoxon's rank sum test or the Mann-Whitney test. Both tests will give exactly the same p-value. The basic idea of Wilcoxon's rank sum test is simple. The null hypothesis states that the observations from both groups are random samples from the same distribution, without assumptions about this distribution. The alternative hypothesis states that the distributions of the variable in the two populations have the same shape, but are on a different location. In the test, the observations of both groups are combined into one group of data, and these observations are replaced by their ranks. If the null hypothesis is true, we expect to see observations of both groups alternately. We will calculate the mean of the ranks of both groups and compare these means. If the null hypothesis is true, we expect the mean ranks to be equal. If the difference between the mean ranks is large, well, this is an indication that the null hypothesis might not be true. So, if the null hypothesis is true, we expect to see blue, red, and so on. If the alternative hypothesis is true, we expect to see the observations of one group located mostly on the left-hand side and the observations of the other group on the right-hand side. Now here's an example with a small data set. The time to pregnancy is given for 6 women in the IVF group and for 5 women in the naturally conceived group. The first step is to order the observations and give them ranks. In this case, the mean rank of the IVF group equals 7.83 and the mean in the naturally conceived group 3.8. Tables exist for the Wilcoxon rank sum test, but SPSS can provide us with a p-value. In the menu of SPSS, choose Analyze, Non-Parametric Tests, Legacy Dialogues and 2 independent samples. In the output, a table with descriptives will be given, showing the same mean ranks as we calculated by hand. The second table shows 2 p-values, an approximation, in this case 0.045, and an exact p-value, p equals 0.052. Based on this last p-value, we will not reject the null hypothesis if we use an alpha of 0.05 and a two-sided test. For small samples, the exact test will be performed automatically. For large samples, only the approximation, the asymptotic p-value, will be given. You can ask for the exact p-value by choosing the option Exact. For the total set of all 193 women, the results of the Wilcoxon and Mann-Whitney test are given here. Based on the histograms, we decided not to use the t-test. The result of the test shows a highly significant result based on an asymptotic p-value. Also, the exact p-value is smaller than 0.001. Based on the table with descriptives, we can see that the women from the IVF group have higher mean rank, indicating a longer time until pregnancy than the naturally conceiving women. If we have to compare more than two groups with respect to a not normally distributed outcome variable, we can use an extension of the Wilcoxon test, the so-called Kruskal-Wallis test. If the Kruskal-Wallis test is not significant, the null hypothesis of equal distributions will not be rejected, and the testing procedure will stop. On the other hand, if there is a significant result of the Kruskal-Wallis test, we can perform pairwise tests to see which groups are significantly different from each other, like the post hoc test after a significant one-way ANOVA. The pairwise tests in this situation are no t-tests, because we do not have normal distributions, but Mann-Whitney tests. SPSS has no option for this, so you have to perform these tests yourselves. Mind the correction for multiple testing in this situation. To perform a Kruskal-Wallis test in SPSS, choose Analyze, Non-Parametric Tests, Legacy Dialogues, and K-independent samples. Here we see an example of the SPSS output for comparing three groups using the Kruskal-Wallis test. We have two IVF groups with mean ranks close together and a group with naturally conceiving women with lower time until pregnancy. The Kruskal-Wallis test is significant, so we know not all groups are from the same distribution. Mann-Whitney tests gave significant differences between naturally conceived and both IVF groups separately. There was no significant difference between both IVF groups. Here is an overview over pros and cons of t-test and ANOVA, so-called parametric tests, and the non-parametric tests. For t-test and ANOVA, there are several advantages. The description is quite easy using means and standard deviations. You can calculate, in an easy way, confidence intervals. And in general, they have more power. A disadvantage, however, is that the p-values are not valid if the data are not from a normally distributed variable. For non-parametric tests, there is an advantage that you can use it for many distributions. It's valid without many assumptions. But disadvantages are that the interpretation is not that clear, there is no clear parameter, and they have less power than parametric tests. If you have doubts whether your data come from a normally distributed population or not, you can perform both the parametric and the non-parametric tests. If the p-values are close, there is not much difference, so you can use the parametric test. If the p-values are quite different, take the p-value of the non-parametric test to stay on the safe side. To end this video, here you see an overview over statistical tests for independent groups. Depending on the number of groups and depending on the type of your outcome variable, you can see which statistical test to use. Please note, these are tests for independent groups. I will introduce statistical tests for dependent or matched groups in another video. Now please make the exercises of video 8 and check your answers. See you in another video. Good luck!